Okay, continuation. Sorry about the technical difficulty. Here we go. We see the free body diagram of the cart. So we'll see something, guys. Remember, we have our 2F net formulas. Hopefully this is not too traumatizing to you. No, the 2F net formulas. Yes, the 2F net formulas. Fnet equals the sum of your forces, and Fnet is, you said it, somebody, whatever, MA. So I'm just going to add up my forces. Oh my goodness, these two cancel out. We're on a horizontal surface. Horizontal surface, remember, now, this doesn't always happen, but a lot of times in horizontal surfaces they cancel out, and looking at the situation, I will say they cancel out. So that means that if this equals Fn plus Fg plus FAPP, these two cancel out. Bam, bam. So you're left with, for the first formula, Fnet equals FAPP. And now you can just substitute your mass and your acceleration. So you end up getting FAPP equals ma. Okay, do I have those things? Well, yeah, I got its force right here. That's the force applied. And this is the mass of my cart. So I just take these two values and I plug them into this formula. So I guess if I wanted to, I could go FAPP, divide both sides by m equals a. So I take that and go over here. This divided by that. Good, good acceleration. Now, how much work, if any, has he done? Well, remember, work equals force times distance. You take this force applied, multiply by the distance the cart moves, and voila, you've got it. Excellent. Now, work and energy. Now, if you've noticed, work and energy have the same units, joules. And now we have work equals force times distance, or displacement. I keep saying distance, I'm sorry. And it equals delta ET, the change in energy. Now, ET is our total energy, or I also talked about it yesterday. I'm actually kidding you a little bit. It's not quite total energy. It's more of what we'd consider to be more specifically mechanical energy. Okay. So the more work you do, the more you change energy. Now, the thing I really want to stress right now, guys, though, is energy. Take a look. Force times displacement, it can have a value. Your change in energy can have a value. I'm sorry, I'm not saying it wrong. Force times displacement, they are vectors. They can have direction. And your change of energy can have direction. So that means it's a vector. Work is a vector. You can have positive work and you can have negative work. Let's think about this. Changes in money. If you found $5, you have a positive change in money, positive $5. If you lose $5, you have a negative change in money. You have negative $5. Okay. Oop, that's not where I thought I was going. Um, the effect of work. Whenever you do work on an object, you change the amount of energy that an object has. Positive work increases the total energy of an object. Negative work decreases the total energy of an object. Two basic types of work. Work done against another force. When you do a push-up or you oppose the force of gravity, maybe I'll clarify that in a moment. I don't know exactly. This is an old thing. So when you're pushing up, you're actually doing work against a force. You're giving yourself potential energy. You're overcoming the force of gravity. You push down to go up. So you are providing work that opposes another force. Work done to change the speed of an object is getting to a car to accelerate or decelerate. So that's another interesting thing. So we've got a couple of different types of work. Make sure we've got these in our notes. You can pause the video. The push-up, you're actually producing a force that goes against another force. Well, what about work and time? When we discuss work, we only concern about force and displacement. There's no longer mention of how long it takes us to complete a task. If you walk up the stairs or run up the stairs, you do the same amount of work. So you have the same change in potential energy. So guys, that's very important. So like let's say somebody walks up the stairs and somebody runs up the stairs. You're going to have the same change in potential energy because you have the same change in heights. So let's clear this out. Be gone, be gone. So let's say we have just a ramp, because that's easier because drawing individual stairs is annoying. So let's say that we have a person, we have 2 points. We're going to label our 2 points at the end, B and A. I don't want that. So let's say a person, hey there, this person, pretty messed up legs. You can do it, kid. All right, they are going to go up this ramp, okay? Now, they could either go slow or they could go fast. They could go either way. Well, what's the difference? Well, one, they change the amount of time the task happens, but they don't change the amount of work that happens, because work is only change in energy, and we would just simply identify this one as the change in height would determine your change in energy. So the velocity doesn't matter for work, which is a tough concept to grasp. It would matter for our next topic, but for work it would not. No matter how fast you determine how you fast you complete a task with work, it does not change its value. So we have to have another term to talk about work. And what we're going to talk about next is power. Now, this didn't turn out as well as I'd hoped, but power is a rate. So power is the amount of work in a given time. So how powerful something is how fast they can do work. The more powerful you are, the faster you can accomplish tasks, the faster work can be done. And the unit for work is going to be joules divided by seconds or watts. There's a very interesting story about that. Talk to more about it later. So what was watts? Well, there we go. The unit of watt was named in honor of Watt, in honor of James Watt. Now, he developed the steam engine, and he basically wanted a way to compare the amount of energy, the amount of work his steam engine could do to other things. So when you want to compare two things, like if I wanted to compare two students, you have to find quantifiable values. And so he tried to see how much work his steam engine could do, and he compared it to the resident um, source of power of the day, which was the horse. So he took his steam engine and compared it to the horse. Very interesting. And he actually didn't start off using watts. He wasn't that big a jerk and didn't name it after himself. He started off comparing it in terms of horsepower. And he started designing engines that had 1 or 2 horsepower. And that's how he sold that. That's like, look, this engine can do the work of 2 horses. Interesting. Here we go. Here's one last one. And we say calculate the power exerted when a 700 Newton barbell is lifted 0.5 meters in 1.5 seconds. Well, we don't really have a whole lot of power formulas. Power equals work over time, which equals force times distance over time, because remember, work equals force times distance. You could also even write it as delta E over T. That's something interesting to think of. And so we could also, if you think about this, d over t, what's d over t? That's velocity. So power also equals work or force times velocity. That's pretty cool. But we only really care about this one. This is the one we're going to use. There's our force, 700 times 0.5. That's 350. So once again, what did I do? I go 700. I'm leaving off my units because I'm being lazy. I don't know what I'm doing. 700 times 0.5, because that's this times this, divided by my time, 1.5. Well, I think the top is going to be 350 divided by 1.5. And I'm trying to do this in my head real quick, and I don't think I'm coming to an answer. So I'll leave it up to you guys with the calculators at home. Hope this is informative and entertaining.